Thanks for coming out today. My name's Andrew Santoro. I'm a dev manager at Macy's. And with me are Peter Connolly and Yvonne Ukolov. And we're going to talk about our experience with Cassandra at Macy's. First, I'm going to talk about background of our application and some problems that we had, which has led us to Cassandra. Peter's going to talk about the options that we explored along the way and how we migrated. Yvonne's going to dive a little deeper into some of the data models that we tried along the way and what worked, what didn't work, and why. And then we'll sum it up with some things that worked and didn't as well overall. Okay, so we're a services application providing REST APIs. What we provide is catalog, store, or inventory data to the website, to mobile applications, store applications, and some partners. We're not doing any big data or analytics stuff yet. We're focused on highly scalable services that can take lots of requests, low latencies, and horizontally scalable. So business has been going well at Macy's. They challenged us to grow the catalog by 10 times and move from what was mostly a batch update where we did read most of the time to a more mixed workload where we're taking a lot of real-time updates and move into multiple data centers. So based on some problems we were having, we had a suspicion that our existing application would be a problem and wouldn't be able to meet those challenges that we had. Some problems we had was a heavily normalized relational database. Believe it or not, we had 51 tables with 4 unions that we had to read to load a complete product. And for certain products, that could be seconds in response time just from the database level, not from the application tier. So we put some caching in front, thought that would solve it. We started with local caches, but as our application scaled out, we were still putting a lot of load on our database. So we moved to a distributed cache that limited the numbers of requests into the database, but still from a front cache on the actual application servers to the kind of data grid tier, there was a big difference in latencies. And the other problem was that when we had these large batch updates we were doing, we would be purging a lot of objects all at once, which led to stop the world garbage collection pauses. We also had some operational problems. When we had this narrow window of time to get the data loaded up for the next day and the latency between the front and the back caches, we decided to preload things into memory. But that was limited because of a short window. If you grew it by 10 times, only a small percentage of your catalog would be preloaded. And the second problem was that if we had data issues and it took that long to load all this data into memory, you had no way to recover. So what we did was kept 2 versions in memory. If you had those problems, instead of starting from scratch and having to lazy load during high traffic volumes, you could switch back and forth. This complicated a lot of release processes and keeping inventory in sync and data in sync between the 2 different cache clusters. And also using a proprietary cache would have been really expensive to scale out. So what we ended up doing was doing a proof of concept on those large data sets and large number of near real-time updates. And we confirmed our suspicion that our app wouldn't handle it. So on to how do we solve that problem. And Peter's going to talk about some options we explored.
Hi, everyone. We were at a unique point in our work there in that we had been experiencing growth of 30% year-over-year organic growth on our website. When I started in 2012, we saw revenues go from $2 billion a year to $3 billion a year, and then continue on towards $4 billion. So the growth was phenomenal. And as Andrew pointed out, we were being challenged by the business because of our omnichannel efforts to grow the catalog and grow the ability to serve that catalog beyond what we had even anticipated with organic growth. So it was one of those kind of disruptive moments in our history there where we knew we had to do some fundamental changes. We were on relational technology. It had to be fronted with a in-memory data grid. Making any sort of foundational database change is expensive. So in terms of options that we looked at, of course, the very first thing off the bat would be, well, we can denormalize our relational database. And how many of you here have actually been through an exercise of denormalizing a relational database for performance reasons? And I'll bet you were profoundly dissatisfied with that effort, just like I have been in the past, and many of us have been in the past. So you can only denormalize a relational database so far, and you're still stuck with a number of different, numerous inner joins you have to do, and performance is always going to be, suboptimal. We're read intensive, so we wanted to look at a series of alternatives to relational that were maybe meet our use case and be slanted towards heavy read during the day and heavy write at night. We probably looked at a dozen different things, and by looking at them, I mean we researched them, we evaluated the features, and this was back in the day when Cassandra was one of many, and it wasn't real clear who was going to be the front runner. So we had a lot of questions, and we would bring in vendors one by one and say, make sure that we understood their architecture, understood the strong points, the weak points, and we're not the federal government, so we had to get to a kind of cut to the chase quickly and say, well, we need to benchmark it, we make sure that this technology works in our environment with our use cases, but we had to get it down to just the short list. And the short list turned out to be MongoDB. It was very compelling with its JSON document orientation, the sharding, really looked hopeful. Cassandra looked like it was truly scalable and true peer-to-peer, which really caught our eye. And ActiveSpaces, which you probably haven't heard of before, it's a TIBCO proprietary in-memory data grid. But it was on our short list because our colleagues in the Macy Systems and Technology Organization have a deep relationship with TIBCO, and they wanted to try it out. So we included that on the short list. The way we did a test, a benchmark, I don't want you to over-focus on the actual performance numbers, because this is more than just looking at a bake-off on performance numbers. We looked at what happened when you took nodes out of a cluster, what happens when you put them back in, how long did it take to snapshot, to back up, to recover, things like this. So it was across the gamut. We looked at a lot of different aspects to this. But in terms of hardware and the actual POC benchmarks, those were run on Amazon EC2. We used the same 5 servers for all 3 tests. They were C3.2 X-large instances, which I mean, you can read too. It's a 8 CPU, 15 gig, 2x80 SSD configuration. And we, if you're in the middle of this type of evaluation, I recommend that you look at your specific business use cases. This was heavily oriented towards inventory, which is very, very high volume, small rows. And we were doing a baseline from production. We scrubbed it, but the baseline was around 150 million rows that we were trying to load and then access. A lot of numbers here. First row is initial load, and this is the 150 million rows that we load. We were achieving around 65 to 72,000 TPS for TIBCO and for Cassandra. I should have mentioned, sorry, we had the vendors for these, TIBCO, DataStax, and 10gen. Remember 10gen? They were all on site helping with these benchmarks. So when we say that we could not complete the MongoDB loads, that was in spite of the help of 10gen. We couldn't complete those. You see that the upserts, the write activity is around 4,000 TPS, 3.2 millisecond, 3.57 millisecond latencies on active spaces in Cassandra. So they're neck and neck. You see this happening all through the benchmarks. And then for read, we didn't do a lot of tuning there, but we saw that we had pretty much even performance between, again, active spaces in Cassandra. So it was basically now a bake-off between those two. This is more just to show you the various types of criteria you should consider when you're evaluating these. Maybe that's not as necessary now. It really looks like, we saw this wide open space of different vendors that had NoSQL offerings, but now only a few are really kind of left standing with really big followings, Cassandra being one of them. But if you were to do this, these are the types of categories and criteria you might look at to say, how should I evaluate this? And your mileage is going to vary because you have different use cases, and this is not something you just take and say, well, Macy's.com did this, so we'll just do the same thing. I would recommend against that. So this is the kind of the core of how we change the engine in the middle of flight. We have a fundamental piece of our business, the catalog, and we can't just kind of throw the other one out, the old legacy one out, and then hope that the new one works on the first try. Apologies for these diagrams. They were very wide end-to-end diagrams, and I wanted to chop off the portions that didn't really apply to the Cassandra migration, but there was a series of phases that we went through to accomplish this without rocking the boat. This just shows kind of the starting point. We had our in-memory data grid, a relational database feeding it. We had store inventory being sent via event queues and a messaging service that was loading that into the data grid during the day. And then we have our old monolithic services serving all this, and those services were Hessian, which is a standard. It's a binary HTTP standard, but kind of presumed that all of the traffic that went to our services tier at Macy's.com would be buffered or shielded by the presentation applications. And so this whole project was done in the context of another project that was modularizing our monolith, this catalog service being one of the first of those, and moving to RESTful interfaces. So that forced us to actually support RESTful and Hessian so that we could be changing the volume between the two, the old and the new stack, and being able to say, is it functionally working? Are the NFRs in place, the latencies? And so we had to do some extra programming to make sure that those services existed on both platforms. This one here is now the phase where we introduced Cassandra into the mix. And now at this point, we're loading the Cassandra data in from the relational database. And we did that because it's kind of a cheat. It was a short-term thing. The idea being that we already had the requirement to load our in-memory data grid from this relational database. Might as well steal that code. That was Yvonne's approach, and it saved us a lot of programming time. We took that same extract and loaded it into Cassandra. So that helped get us into production quickly and try this out. And you see the addition of new catalog messaging to handle the store inventory, and new catalog service to handle the REST JSON that was going to go directly against Cassandra. Notice the use of a load balancer there so that we can tweak the amount of traffic that's going to new versus old. So we weren't just going to turn the spigot on completely all at once. And that being done, we could then turn the dial further and further to see how it handled more and more volume. This next one is just adding additional capacity. Having done the pilot, seeing that it worked, we started moving all of our product feed and our fulfillment, our online fulfillment inventory feeds into this and adding additional capacity, using the F5 throughout to kind of tune in and see how well it was working. And then once that was there and stable, you see we can just basically get rid of the catalog footprint of the relational database, the in-memory data grid, and now it's just Cassandra, the catalog messaging, and the catalog services. So this is just a final diagram to show kind of how we had the switch from, on the left, the old legacy services servicing most of the traffic, and then on the right switching over to the 99% plus, 100% of the traffic going to the new catalog services. Next, Yvonne is going to talk to you about data models and performance. Thank you. I think I went over.
Hi, everyone. So there were several use cases we needed to implement on Cassandra. Today I'm going to talk about one use case which actually required us to model hierarchical data in Cassandra. You can see simplified domain model on the slide. Basically, there's product object which has such attributes like name, description, shipping information. There's one-to-many relation from product to its attributes used by merchandising managers to trigger various business rules around how to show product on the site and other selling channels. There's one-to-many relation from attribute to attribute value, and value itself is a composite object which has effective expiration date, status, which could be enabled, disabled, archived, and so on. There's one-to-many relation from product and UPC, and in our data model, product has some common information for sellable items, and UPC is basically UPC is a sellable item, which it has combination of color and size, availability information online, and in stores, price information. So there are many such one-to-many relations, nested relations, which start from product. We wanted to aggregate the data in such a way to minimize number of reads. Ideally, we would like to read all that information by single read operation. We wanted to avoid reads before writes for relevant use cases to leverage high write throughput of Cassandra. And we wanted to keep all the data we store in Cassandra in clear text, so that if there is some issue with service response, we could directly connect to Cassandra, see maybe it's, and kind of clearly identify is it caused by data issue or there is some defect in business logic and application layer. Back in 2013, it was new release of Cassandra 1.2. It had collections, compound keys, and so on. So first data model we tried to implement that was based on what we call parallel lists. Let's consider that example on the slide. There's product entity which has ID and name fields. There's one-to-many relation to UPC, and UPC has ID, color, fields, and product ID, which is foreign key to product. UPC has one-to-many relation with attributes, which has ID, name, value, fields, and UPC ID, which is foreign key to UPC. And how it works is ID and name fields of product, they go as is to their product table in SQL because they belong to top level entity. ID and color fields of UPC, they go into UPC ID and UPC color lists in such a way so that ID and color of the first UPC, they become the first elements in those lists. ID and color of the second UPC, they become second elements in those lists. And similar way it works for attributes. In such a way, we could represent infinite number of such nested one-to-many relations, theoretically. And in general, this data model kind of solved over all our requirements we had. Like we represented hierarchy, obviously. We could read all the thing by product ID, which is partition key here. It's in clear text, although we couldn't do update before without reads, because, for example, if you want to change color for UPC with ID 33, we don't know whether it's second item on the list or the first item element in those parallel lists. So we would need to read it first and then issue update operation. To overcome that issue, we thought about using maps. In maps, you could easily update, for example, color for UPC with ID 33. To do that, you need to know product ID, which is partition key. You would need to know UPC ID, which is key in UPC color map, and new value of color. And you could apply update operation without reading that row first. So in general, collections-based approach looked fine at the beginning, although we faced some issues with those collections. Back in 2013, as I mentioned, we started with 1.2 version of Cassandra. It had just brand new version of native protocol. And by the way, it's applicable to version 2 too. So at that moment, collection could not have more than 64K of elements, and each element in collection cannot be bigger than 64 kilobytes. Recently, in 2.1 version of Cassandra, there is third version of the native protocol, and those limits were increased. Now, there are 4 bytes used to encode collection size and length of each element. So theoretically, like that could be leveraged. Although I wanted to mention that there is still 64K limit for set elements max size and map keys max size. And also, official documentation from DataStax doesn't recommend going above 64K for any collection type. So kind of you can use it at your own risk. Just wanted to briefly go through why there's still 64K limit for set elements and map keys. Let's consider this example. There's a collection table which has 4 columns: my key, my set, my map, and my list. And I insert sample data like 2 integers, 1 and 2 into the set and the list, and 2 entries to the map. So internally, we know that like each piece of data in Cassandra is stored as a cell, and each cell has cell name, cell value, and timestamp, some other attributes too. But those are kind of major things. And you can see highlighted in red, set elements as well as map keys, they actually stored in the cell name part of the cell. And highlighted in blue, those are list values and map values part of entries. And in the internal storage, there's actually 2 bytes allocated to encode cell name. That's why, even though native protocol supports longer set elements, that limitation still comes from kind of internal storage structure. Also wanted to mention that hexadecimal string in bold, that's 16 bytes used to maintain order of elements in list. And that may be pretty significant overhead if you store some small values in list like integers, which is just 4 bytes. Third data model we tried was based on compound keys and JSON. In general, JSON is an easy way to represent hierarchy. It supports it naturally. The only question was, do we want, like, how granular it should be? Do we want to put everything product with all its attributes, UPCs, and everything into a single big JSON object? Or it should be more granular. Based on our written update patterns, we decided that the best way to split it would be to have a JSON object for products and separate JSON object for UPCs. Next question was, how do we express relations between those? And we used compound key to do that. In this table, there's 2 fields which are part of primary key: product ID, which is partitioning key, and UPC ID, which is clustering key. Object field of type text, which can store either product JSON or UPC JSON based on value of UPC ID clustering key. So that if UPC ID equals 0, that means that SQL row is product row, and we store product JSON there. Otherwise, if it's a positive number, which would mean would be actual UPC number in that case, that SQL row would be UPC row, and object column would store UPC JSON object. So that data model also worked fine. Like, we represented hierarchy thanks to JSON. We even got some more flexibility how we can read and update it. We could read product and all UPCs all together by just partitioning key, or if we know UPC number, like by product ID and UPC ID, we could read just JSON, just UPC object, or just product object. So one question was, since we use JSON, it doesn't support partial reads on updates. If you want to change some small piece, let's say in the product JSON, you would need to read full JSON for product first, apply your mutations, and then store it back. For our case, actually, for such cases when we needed partial reads and updates, we just extracted that information to separate column, like review column, fourth column in the table. Like review column, it stores customer ratings data, and that comes from different sources. It has different life cycle. So we just put that into a separate column, and that was fine with us. We could update it without touching product data. So when we had those alternative data models, we ran some performance tests to see what works better. One of those tests was data load test. Basically, criteria was how long does it take. Performance test consisted of 3 data loads. There was data loader component, which was loading data from relational database, was assembling data in such a way so it could be written to Cassandra. There are such 3 data loads sequentially with 10 minutes between each. And as you can see on this chart, data load for collections-based approach was taking 5 times longer for first and second run. And it took even longer, 10 times longer for the third run. Based on these performance results and based on collections limits back in 2013, we decided that compound key JSON-based approach works better for us and went with that approach going forward. Few thoughts on why we think there was such huge difference in performance. First of all, with collections-based approach, that approach produced hundreds of thousands cells per partition key on real data. For example, like if we have product with 10 UPCs, so to store all those 10 UPCs, we would need collection of size 10. If each UPC has 10 attributes, to store 10 all attributes of all UPCs, we would need collection of size 100. If each attribute has 10 values, then to store all the values of all attributes of all UPCs, collection would be of size 1,000. And as you know, each element in collection produces separate, it becomes a separate cell internally in Cassandra storage model. So second reason is storage overhead. There's a formula could be used to calculate size of each cell. So for regular column, it's column name plus column value plus 15 bytes. In case of lists, as I mentioned earlier, there are 16 bytes encoded into column name to maintain order, so it's additional 16 bytes plus your column name. So, and let's say if you store something small as like product ID or attribute value, which is just few bytes, you can pay maybe like 40 bytes of storage overhead to store that data. So it's really a bad ratio of storage metadata and payload. And for JSON-based approach, it's much better because if you store something like 10 kilobytes JSON object or 100 kilobyte JSON object, you don't really care if there's some extra 30 or 40 bytes of overhead. Just to summarize, based on our experience, we think the JSON-based approach works better to store hierarchical data because there's better ratio between storage and payload. It has direct correlation with throughput and latency of both read and write operations. It supports hierarchical structures. It loses in partial reads and updates, but there's workaround. You can extract, like in some cases it works, in some it doesn't. But in our case, it worked fine. In that case, we just extract data into separate column. Also wanted to mention that it complicates schema versioning because without JSON, you care only about SQL schema. But if you have JSON, which evolves over time with your application, you need to take care of proper versioning of both SQL schema and JSON. Also, there's user-defined types, which were introduced, I think, as part of Cassandra 2.1, which might be a good option, actually, to express such hierarchy, because now UDTs, then they can have column types as collection, and collection can be of type of another UDT. So you can use them as a nested to express nested structure. But we haven't tried that, so just wanted to bring that to your attention.
Okay, just want to quickly summarize, I know we're running out of time, the overall journey we had. What we thought worked really well and what was good was the documentation for Cassandra is really good. DataStax was very helpful along the journey. CQL3 is very easy to learn coming from a relational background. Query tracing, very useful. It's been stable. We've had very few production incidents. And the big one for me was able to simplify our architecture, reduce all the caching mess that we got into, but still get the same performance. For development, Cluster Manager was great. Highly recommend that. Some problems that we had. SQL queries brought down our cluster, and that was by using large limits. Luckily, that wasn't in production, but it was still kind of surprising that a query could take out your whole cluster. We had deleting and creating key spaces without truncating them first. We were able to load data, but then when we tried to read, there was references to old files and file IO exceptions. Like most people, like compaction dealing with tombstones was a learning process, and we definitely learned a lot from that. We were clustering a lot of data that shouldn't have been, so those nodes in particular took days to finish compaction. As Yvonne talked about, your data model that you used, you need to understand the underlying storage behind it to optimize your performance. We've had a few problems with drivers. We're using 2.1.4 when we're doing rolling upgrades of the cluster. One wouldn't come back. We took it out. The driver didn't really understand that node had left. And monitoring performance with Off Center, we ran it was hard to get like average values when your peaks are so high, but they've gotten a lot better in the most recent version. Some of our own problems that we've had, we have a small cluster but kind of beefier machines, and that requires that all your servers perform really well rather than having a larger cluster of smaller machines, which probably would have been a better from the outside. Again, what Yvonne was talking about was versioning in the JSON schema. You got to make sure your version is backward compatible. We found that problem of we updated it, we could write to it, but we couldn't read. We like to export production data to use in different environments. We've found that that's a very expensive operation, causing jumps in CPU. Non-primary key access was difficult. We usually do lookup tables. And then we have a lot of test environments for merchants to look at what way the catalog is going to look on a different day. And we have so many that we try to keep them small, but still have the same data size. And that's been a real challenge. Some future stuff. We started on 403. We actually did go up to 465. We want to do conditional updates based on column timestamps coming to not have to read before you write again. And that's in 4.7. We want to do DSE Spark for some reporting and analytics on our data, like finding out which brands or which sizes or which colors are running low on inventory. That's something that was very easy in a relational database, but now we're just doing primary key-based reads. That becomes a challenge. We have split into multi-data centers, but we're not replicating yet. They're kind of totally isolated. We want to replicate properly. Managing the schema with MuteGen, our relational database. We used Liquibase, and that worked well. We want to do that. We want to try to figure out how to solve the JSON schema versioning. We'd like to use RxJava so we can asynchronously load different components of the products, like reviews and inventory, and then have it reassembled after. We think that will improve our performance. And we use Spring a lot at Macy, so explore some Spring data. A few things we'd like to see. We'd like to see for the reporting stuff like a Kibana on top of Elasticsearch. We did talk with DataStax, and I know they played around with Banana, which is the same UI on top of Solar, so that might work well. When we move to a multi-data center model where we actually do replicate the data, we have some use cases where we need to notify our consumers that like inventory changed. So we don't have a current way to know that one product finished replicating. So we'd like some kind of listeners on that. And moving to an omni-channel, we actually have a lot more data that resides in different stores and being able to search geospatially. Okay, and as usual, we're hiring. We're in San Francisco. We also have some offices in Atlanta and Boise, Idaho. So if you're looking for work, we'd love to have you. So thank you. And there is one final thing I'd like to mention is that I know a lot of people here know Patrick. I hope you saw him blending Raspberry Pis at the keynote. We've identified that we think he has a secret identity. And it was Peter who figured out his secret identity. We want to expose it right now. So he's Buddy Pie. All right, so we have 3 minutes for anybody who has any questions. Right there. This guy's got a microphone. He'll come over. You guys want to hop up? Hop up.
Have you guys done any performance testing with user-defined types? I don't think.
We haven't at all. Like, we just would like to start playing around with it, but that's kind of a next step. That's on our list to do. Haven't attempted. Anybody else? Right here.
In your example, you gave us a 3-level hierarchy as an example. How deep were you actually in your data model? How deep was the hierarchy and where it started failing? I know the 64K was thrown around. I just wanted to know.
I think we only, and that was a sample, I think we only go 2 levels deeper than that, master member.
I would say maybe like 3-4 levels deeper.
Yeah.
Okay. And it was intentional, or it was just for the sake of performance reason you kind of do it that way, or your data model will be sufficient with 5 levels?
You mean intentionally why we had so many nested relations? I mean, that was data model which we used in previous data store, which was relational. So there are some established entities and relations between them. Those are used by machine learning managers to set up business logic. It's kind of all business logic is data driven. So it's easier for machine learning managers to express like what they want, how they want to show products on site, to give them the best flexibility they want. Like that data model is used to support that. And it was technical challenge then how to support that on Cassandra side. So we had to stay with those relations and nested attributes, entities.
Thank you.
Right behind you. Okay.
You modeled your catalog in a hierarchical way in some entities, right? Now, your multiple devices have different requirements on what attributes to show or how much information you want to show on which page, depending on you're on the product details page or on the checkout or wherever you are. How do you handle that? Do you filter out all the data in the application, or do you store multiple copies of it?
So let's see. That's right. So for example, category browse page, it shows kind of smaller aggregated version of product, right? And on product details page, there's big product image and so many details. We actually supported both those use cases using a single table. So every time we read the whole thing from Cassandra, although we separated kind of dynamic and more static data. So whatever is driven by availability was kept separate. And we cached all that information in application layer, in local caches. And there was just some business logic we were applying on top of that product data. We were aggregating something and could return like different data based on request type.
All right, one more. I think we
Yeah,
have
hi.
time.
So in your JSON and the compound key example that you had for the second data model, you mentioned there's a lack of indexing besides the primary index to pull out data from your catalog, for example. So one suggestion I have, I don't know if you guys explored that, is DSC Cassandra has Solr integration with it. So if you have the right columns exposed, not your entire JSON document, you could index on those columns and get the data quicker.
Our on-site search was based off of Solr before we moved to Cassandra. So we do try to just get mostly by primary key based on queries through Solr. But yes, like getting the catalog itself, aside from like keyword searches and browses and facet counting, it would help.
Yeah, just would like to add, like in that case, in that particular case, I think I was talking about partial reads and updates, not about indexing. So I mean, we are fine with reading data by kind of partition key for that data model. And as Andrew mentioned, there's separate search system used to.
So we're getting cut off, but we're happy to hang out outside. If anybody has more questions, please drop by. Thank you.
Thank you.